this question, we are told that someone is going to throw a ball off the top of a building, and the ball is going to land a certain distance away. Now, this is an example of 2D kinematics. Photo 1 is going to correspond to where the ball was thrown, so a nanosecond after the ball was thrown, and photo 2 will be a nanosecond before it hits the ground. Now, we are now going to write down what are all of the things that are, almost forgot. We have to set the origin and the axes. I'm going to set upwards as being positive y, rightwards as being positive x. So, let's list out all of the things that are known in this question and all of the things we have to find out. So, the displacement in both directions is known. We were told that the building was 60 meters tall, so the vertical displacement of the ball will be negative 60 j hat meters. And the horizontal displacement, we were also told. We were told it lands 100 meters away. The initial velocity of the ball. We do not know what it is in x, but we were told that the ball was thrown horizontally. That is a synonym for saying that the initial y velocity was 0. The v final is not known. That's going to be one of the things that we find out over the course of this question. But the acceleration is known. The ball is not in powered flight, so there is no x acceleration. That would be 0 I hat meters per second squared. And the acceleration in y would be the usual negative 9.81 j hat meters per second squared. The time also is unknown. Now, for this question, we were asked to find the time first, followed by the launch velocity, followed by the final velocity, and then the final velocity has to be turned into polar. So, let's do these in order. First, the time. We have 2 pieces of information in x, not enough to use the toolbox equations. But we do have 3 pieces of information in y, and that is enough to use the toolbox equations. So let's go ahead and solve for time using the information in y. We have displacement, initial velocity, and acceleration. We're looking for time. There's only one equation that weaves together all those quantities, and that is toolbox equation 2. That is delta y is equal to v initial times t plus 1/2 acceleration times t squared. So delta y, negative 60, is equal to v initial times t, so 0 times t plus 1/2 acceleration, negative 9.81, times t squared. Now 0 times t is going to cancel out. And half of negative 9.81 would be negative 4.905. So simplifying, we get t squared is equal to negative 60 divided by negative 4.905, which is equal to on your calculator it might be a bit different. I'm going to put parentheses just to be on the safe side. Negative 60 divided by negative 4.905. 12.23. And t, the time, would be the square root of that, which would be square root of 12.23 is 3.5 seconds. So that is the time required for the ball to fall to Earth. What about the launch velocity? Well, now that we know the time, we also know the acceleration, we know the displacement, we're looking for the initial velocity. So the initial velocity would be solved using exactly the same equation, because toolbox equation 2 is once again the only equation that weaves together these 4 quantities. So delta x is equal to 100, is equal to v initial, which is unknown, times time, 3.5, plus 1/2, acceleration is 0, times time squared. I'm not even going to bother writing out the time squared because it's multiplied by 0. This whole term is going to cancel. So we get that V initial is equal to 100 divided by 3.5, which is equal to 28.57. And that would be in I hat meters per second. So to summarize what we've seen so far, the time required for the ball to land is 3.5 seconds, and the thrown velocity, the initial velocity of the ball in the x direction, was 28.57 I hat meters per second. Now we need to solve for the final velocities, and then we need to convert them into polar. So for the final velocities, let's start with y. In y, we have so much information that we can use any of the toolbox equations to solve for the final velocity. I feel like going with toolbox equation 4 today. V final squared minus V initial squared equals 2 times acceleration times delta y. So V final squared is unknown, but V initial squared is 0 squared is equal to 2 times an acceleration of negative 9.81 times a displacement of negative 60. So let's solve that out. 2 times negative 9.81 times negative 60, 1177.2. So 0 squared, of course, will cancel out, and we are left with V final squared is equal to 1177.2. Then we just take the square root, 34.31. So the final velocity in y is equal to 34.31 j hat, and I actually made a mistake just now. Why? Because it's descending in y. So correctly, I need to say negative 34.31. When you take the square root, there's always a positive root and a negative root. In this case, because it's descending, we need to use the negative root. We said upwards is positive, so descending must be negative. What does that leave us with? It leaves us with the final velocity for x. Now, if you really wanted to, you could solve this using the toolbox equations, but there's really no point. The acceleration is equal to 0, and so that means that the velocity didn't change. So in x, unlike in y, the final velocity is going to be the same as the initial velocity, 28.57 I hat meters per second. So negative 34.31, that was the solution to part C. Part D was basically asking for the overall velocity. So the overall velocity is 28.57 I hat minus 34.31 j hat, which we could write like this. Now the last thing to do is to convert this into polar. So we start by finding out what is the size of this final velocity. We do that by applying Pythagorean theorem. So you take the square root of 28.57 squared plus negative 34.31 squared. So 28.57 squared plus negative 34.31 squared gives us 1993.421. Then we take the square root of that, and we get 44.65. So the overall velocity in polar, or I should say the overall speed in polar, was 44.65 meters per second. Then that also leaves the direction to be solved for. So the direction, that's theta, is going to be given by, so this would be the r in polar, this would be the size of the vector, and the theta would be given by the arctangent of y over x. So y, negative 34.31 over x, 28.57. So arctangent of negative 34.31 divided by 28.57 is negative 50.26 degrees. So we could say that the overall velocity of the ball, just as it's about to hit the ground, is 44.65 meters per second at an angle of negative 50.26 degrees. That is 50.26 degrees below the x-axis. We'll start by drawing a picture. Here's an eagle. I'm not going to apologize for that. You already knew what my limitations were coming into this class. And here's a fish which is going to fall into the lake below. So our initial photo is going to be an instant after when the eagle loses contact with the fish, and photo 2 is going to be an instant before the fish hits the surface of the water. I'm going to set upwards as positive y and rightwards as positive x. So let's think about what are the things that are known and what are the things that we need to find out in this question. So we were told that the fish had to travel vertically by 5 meters. Now, because that's the negative direction, that means that its vertical displacement is negative 5j meters. The fish was originally not moving in the vertical direction, but it was moving horizontally because it was moving along with the eagle. So that means that because the eagle was moving horizontally, there is only a horizontal component, and that was 3 I hat meters per second. There was no vertical component, so its initial velocity there is 0 j hat meters per second. The final velocities are unknown, and the acceleration would be the usual 0 I hat meters per second squared for the fish in the horizontal direction because it's not in powered flight, and negative 9.81 j hat meters per second squared because it's falling, and we set gravity as being, gravity is always downwards, but we set upwards as being positive. And the time is unknown. So what we are looking for is what the velocity of the fish was going to be just as it hits the surface of the water. So that would be the final velocity here and the final velocity here. So let's start by solving for the final velocity in y. In y, the final velocity would be given, there's only one equation that weaves together these for quantities, and that is v final squared minus v initial squared equals 2 times acceleration times delta y. So v final is the thing that's unknown, minus v initial, which was 0, is equal to 2 times negative 9.81 times delta y, which is negative 5. So v final squared is equal to 2 times negative 9.81 times negative 5. That 2 times 5 is 10, so this whole thing will work out to positive 98.1. And the square root of 98.1 is 9.9 meters per second. So that is the velocity of the fish in the y direction. And I should actually be a little bit more careful here. It's falling, which means that this is actually a negative velocity. Now, what about in the x direction? In the x direction, we only have two pieces of information, but if you think about it for a second, we're told that the acceleration is 0. Acceleration is a change in velocity, so that means that the velocity wasn't changing. So you could just as easily say that in the x direction, the final velocity is equal to 3i hat meters per second, and you could stop there. This is something that you're allowed to do only because the acceleration is 0. You would get the same answer if you actually went through solving the toolbox equations, solving for time, then using time over here. But I think that's pretty pointless, because if you're told that the acceleration is 0, then you only run the risk of doing extra work and making more mistakes if you don't use that information to your advantage. So I'm going to simply say that the final velocity was the same as the initial velocity because the object was not accelerating. The fish was not accelerating.